Okay, I'll start the recording.
Okay.
And it's live on YouTube also. So Sanans, I hope you don't mind having your thing shown
It's
on
okay.
YouTube.
I can always turn the video off if I want.
I know, but like you don't mind others seeing your face and whatever. I don't think you do. So,
No, it's fine. But thank you for asking.
What I know. So okay, let me start. All right. So let's see. Since in the last lecture we started talking about the ADM formalism. Are there any questions so far about what we discussed in that session? So I hope that you all spent some time going over these notes, and I'd also shared these notes on Zulip, so I hope you were able to get them. Anyway, so I'm sure Sundance recognizes most of it.
Yes, this is looking quite familiar so
far. So, and we ended at this Gauss-Kodachi equation. Well, I didn't derive it, but I told you, well, that's the end goal. So, and this is lecture 3, actually. Sorry. Okay. All right. So we have this equation. All right. And so if we now, if you want, I can spend some time in working out the derivation, but I mean, it's just long and tedious. And I mean, you can find it involved in many other references. So I'll give you a brief outline of the derivation instead of just deriving the whole thing. Okay. So let's see. Now, the way we go about this is that we have defined this 3 metric, right? This projector. And in terms of this, using this 3 metric, we have also defined a derivative operator, right? And this is a derivative operator. So you know, again, these are some of the things that you should work through and convince yourself that this does satisfy the Leibniz rule and linearity and so on. And it also is the case that this derivative operator acting on the 3 metric gives us 0. So again, you can prove this by using the definition of the derivative, right? So it's a projection. So HA mu, HB mu, HC alpha, then grad mu, H mu alpha, right? And then for this expression, you can substitute this, and then this derivative operator annihilates the metric. So that part is 0. And then you can just do some, do some algebra, and you will, and also because H annihilates the orthogonal vector, this hypersurface orthogonal vector field, and so the answer is 0. Right. So once you have this, then you can define the associated Riemann tensor. Right. So this is the 3-dimensional Riemann tensor, and it's defined in exactly the same way. But let's define in the way you do it for any manifold. Now again, in this expression, so what we want to do, right, is we want to find out what is the relationship between this Riemann tensor and the 4-dimensional Riemann tensor. So one way to proceed is that we write down, we look at these terms. Let's say we look at this term, the first term in this expression, and we proceed by using the definition of the derivative. So again, so H B mu, H C mu, del mu, omega nu, right? So we take this gradient and we project it down to the manifold. And then, of course, we have to project this guy also, right? So then we get a whole bunch of indices. So we have to take all of these indices and project them. And so, well, you have to take indices. Right. So we have to take these 3 indices and project them down. So we get 3 other factors of H. Then this D, then H, then something like this. I'm not writing down all the indices. All of this is, so for example, if you want, this is all worked out very nicely in Wald in equation 10.2.20. So I have shared all the sections from Wald, by the way, which collectively give you the complete guide to the 3+1 formulation, including the Lagrangian and the Hamiltonian framework. So anyway, you do this and you work through a lot of tedious algebra, and what you find is ultimately these 2 equations. One equation is R, A, B, C, D, right? So you do this, you get some complicated expression, then you anti-symmetrize over the A, B indices, then you subtract, and lots of things cancel out. And ultimately what you're left with is something which looks like, let's see, this 4 A, B, C, D projected down. So again, A, B, C, D, mu, alpha, beta projected down, H, A, mu, H, B, mu, and so on, minus K, A, C, K, B, D, plus K, B, C, K, A, D. And similarly, we can ask what is the covariant derivative, what is the action of the covariant derivative on the extrinsic curvature, and we find this relationship, which is equal to R, C, D, and D. So collectively, these 2 expressions are known as the Gauss-Kodachi. So some places spell this as Kodachi, some places spell it as Kodachi. I don't know which one of these is correct. And I don't think we have any Italians amongst us to guide us in that regard. So I'll just call it Kodachi. And then we can perform some contractions, and right, because we want to find the Ricci scalar. So we perform the usual contractions on these two expressions, and those contractions then they lead us to the expression for Gauss-Kodachi that I had given you in the previous class, which is which I think maybe I made a mistake in the sign. So this should be a minus sign, this should be a plus. Okay. So now the thing is that we can write down the action for the Einstein-Hilbert action by d Newton integral t power x root minus j, and we have this 4 Ricci scalar. And so this becomes 1 over 8 by t Newton d4x minus j, this guy, and then minus KAB plus k square. Okay, so now what we have managed to do is we have expressed almost all the quantities on the right hand side purely in terms of variables which are defined on the spatial hypersurface, right? And I hope, as in the last lecture, I hope that it's clear to you. You have understood why it is that we can express the properties of the 4-dimensional geometry in terms of things which appear to be defined only on the 3-dimensional surface. And the reason is because, well, this is the intrinsic geometry, but this is the extrinsic geometry, and this is the one that contains information on the embedding of the manifold of the hypersurface in the higher manifold, right? Okay. And Professor Haridas has also joined us, and Haridas sir has actually done some very interesting work in spin networks and LQG and so on. Now we have another term here, this root minus g, which is as yet to be expressed in terms of the what do you call it? The hypersurface dependence of this term has not yet been clarified. So you remember that we defined this this time evolution vector field, and this time evolution vector field can be written as a sum of the orthogonal part, hypersurface orthogonal part, and the hypersurface tangential part, right? And this is the lapse function. And this guy is called the shift vector field. So you can think of this as generating spatial diffeomorphisms. This maps the hypersurface to itself, and this vector field generates time-like diffeomorphisms. So it maps the hypersurface. Well, the whole vector field is a time-like diffeomorphism. Now, so it turns out that this quantity root of minus g has a nice expression in terms of the volume element, the determinant of the 3 metric, and the lapse function. Okay. So again, the proof of this, well, I don't have it in front of me, so we will leave it as an exercise for you. Okay. All right. So then we can finally write down the Einstein-Hilbert action in terms of quantities. So then it becomes d4x, and now we can write it as d3x dt n root minus root h. There's no minus because h is a spatial metric and it is positive definite. And this, right? Okay, and this quantity is our Lagrangian now. It's a Lagrangian density. And again, I don't know where these sign errors are coming from. Maybe it's in Wald, maybe it's in something else. I don't know. So I apologize for this. Okay. Now, for the next step is that you go from the Lagrangian. Once you have this Lagrangian, right? The next thing is we want to ask what is the configuration variable and what is the corresponding generalized momentum. So as our configuration variable, we will choose the 3 metric as the configuration variable. Okay. And now it turns out that there is this very nice relationship between the extrinsic curvature and this variable, which is that if you take the Lie derivative of this object, so if you take the Lie derivative of H with respect to the hypersurface orthogonal vector field N, then this is equal to twice, I think there's a factor of 2 here, is equal to, right, 2 times K alpha beta. Okay. Now, this Lie derivative, maybe you are familiar with it, maybe not. So I can go over what the Lie derivative is. I sort of briefly explained it in the last lecture that you know, and if this explanation is sufficient, then I leave it here, leave it at that. Otherwise, I can go over the details. Is there any buddy who would like me to do that? If you are interested in learning more about the Lie derivative and how it's different from an ordinary derivative, you can raise your hand. I see any raised hands? Maybe. No. Okay. All right. So I suppose the feeling is that you all want to get to the meat of the matter, right? You all want to get to talk about loop quantum gravity. Okay. So this can be expressed. So using the fact that, right, we have this expression here for the time-like vector field. Okay. And so this expression tells us that this n mu can be written as in this way, right? And so if you take this Lie derivative, it becomes the Lie derivative with respect to of this H alpha beta. Okay. And the Lie derivative is a linear function. It has the property that if I take the Lie derivative of some tensor with respect to the sum of 2 vector fields, it's equal to the Lie derivative, sum of the Lie derivatives with respect to the individual vector fields. Right? It's a derivative operator, so it should have this property. It also has the Leibniz property. That's another useful thing. So this can be written as the Lie derivative with respect to T mu by n of H alpha beta, and then minus the Lie derivative of H alpha beta with respect to the vector field n. Okay. And all of this is equal to 2 times K alpha beta. Right. Now, from this expression, what we get is we can use the Leibniz rule. So the Leibniz rule for Lie derivatives is as follows. for Lie derivatives. So if you have a vector field V, let's say, and you have some function, which is some scalar field, right? Then F times V is also a vector field, right? So then I can ask, what is the Lie derivative of some arbitrary tensor with respect to this vector field, which is formed by the combination of F and V. And so we have the Leibniz rule, which tells us that this is equal to F times the Lie derivative of t with respect to V, okay, plus what is it? Okay, just let me very quickly look up. I forgot the expression. Right. Okay, yeah. Plus V times Lie derivative of what am I doing? Okay, let me just what was that expression again? Sorry about this. Just copy it. Okay. Paste. Okay. Oh, right. So I was wrong. That's not how the Leibniz rule works. The Leibniz rule works on a product of this thing vector fields, right? So that's the mistake I was making. So we want to ask, what is the Lie derivative with respect to V of F times U? So this is U and V are two vector fields, right? And then we get the Leibniz rule, which is that, right? So this is the usual Leibniz rule which you expect for derivative operators, right? If you have the derivative operator acting on the product of something, the Leibniz rule is written like this. So it's the same rule. It's has the same form, right? Lie times this, and this works for any arbitrary tensor, not just any vector field U. So if you have some arbitrary tensor t, then f of t, so then this becomes f times this t plus t times mv, where f is some scalar. Okay. Now we can apply this Leibniz rule to this expression. So this expression is 1 by n multiplied by okay, so again, mistake there. I guess we can't apply the Leibniz. Well, when you work it all out, what you find at the end of the day is that KAB, or 2 times KAB, which is this HAB, is equal to 1 by 2n, and we have LTHAB minus DANB minus DB. So this first term, it comes from this expression, and the second and third terms, they come from this, the Lie derivatives of the metric with respect to the shift vector field. Okay. Now this quantity is what we identify with the time derivative of h. So you have this spatial manifold, and at sigma t, let's say in sigma t plus delta t, and your time-like vector field is telling you how to go from the first manifold to the other manifold, right? So the time derivative has to be measured with respect to this vector field, right? So we get this expression for KB, and now we can substitute this expression in our Lagrangian, right? For KAB and K square, we can substitute this expression. So we have 2KAB is equal to 1 by 2N HAB dot minus TANB minus TPNA. So then we substitute this in the Lagrangian, okay? And then again we get so the Lagrangian will end up having terms which are proportional to the time derivative of h squared, right? Because the Lagrangian has these terms. The Lagrangian has these terms, KAB, KAB, and K squared, right? So you will get terms proportional to the square of the time derivative of the spatial metric, okay? And there are some questions in the chat which I seem to have missed. What is the vector n shift vector? But there is an n. So this n is a lapse function. This is not a vector. And Devamalya, where is n mu? N mu is over here, right? This is the lapse. Okay. So when we substitute in LG, and then we can take the functional derivative of LG with respect to this HAB, right? And this gives us our momentum conjugate to the metric. And this momentum has the expression. Again, I'll just give you the expression. The calculations are long and tedious, and which may or may not be enlightening for most of you. So finally, what we have is we have our phase space. So our phase space consists of the spatial metric on a 3-manifold and the conjugate momentum. And the conjugate momentum is a function of the extrinsic curvature. So this is sort of like what we expect, right? Because the extrinsic curvature tells us how the intrinsic metric changes. So the phase space, a point in phase space should basically define the full geometry of the system, right? Not just on a given, it should specify the full system, right? And at some initial time. And that's what these two quantities together do. This tells you what is the geometry of the 3 hypersurface. And Devamalya, you can please ask, you can just, yeah, go ahead, ask your question.
Deepak, can you bring the previous sheet? Yes, I just am confused with the notation n capital vector in the expression of the 2k alpha beta in the right hand side in the lead derivative with respect to shift vector. What is the vector sign signifies? Because in the left hand side it is n mu. And what is
all right? So let me write down the definition for the lead derivative once again. Okay. So if you have some vector field, the Lie derivative with respect to for a scalar function is just the directional derivative. Okay.
Yeah.
For the Lie derivative of a vector field is a commutator. Okay.
Okay.
And then you can generalize this to higher order objects. So the Lie derivative of, so here I should be consistent and I should write u of a. That way the indices on both sides match. And so in this way you can generalize this by asking, for instance, what will happen if I take rank 2 tensor and contract it with a vector field, and what is the Lie derivative of that object? And then you apply the Leibniz rule, you expand out everything, and you can find out, for instance, that if you have a tensor field of this form, then the Lie derivative will be AB and then plus HAC grad B minus VC and plus HCB grad A. And so there's a thing I'm missing. Yeah, this would be grad C and VA. Oh, sorry, VA, right. So that's what we are doing here. We are applying this Lie derivative to H alpha beta. And when we apply this Lie derivative, we get these terms. And we substitute for H alpha beta, for HAB, we substitute this expression plus NANB in each of these terms. Then we use the fact that, for example, this term is 0. And of course, the gradient of this delta will be 0, right? And so ultimately what you find is that this is equal to grad A and B. Well, not just grad A and B, but the projection of grad A and B, which is grad HAC HBD del A and B. And there's a factor of 2. And this quantity in the brackets is what we know to be the extrinsic curvature. Okay.
Okay, I understand.
So the thing is that, look, you really have to, sit down and work through all the thorny details. There's really no alternative. And if I did go through all of the details in the class also, it would not necessarily make any difference. So. Any other questions? Okay, so now we can define the Hamiltonian. And the Hamiltonian is given in the usual way by the Legendre transform of the Lagrangian. Okay. So now we have our expression for pi AB. We can substitute this. Over here. And then what is this H dot? Well, for H dot, again, we want to use this expression for H dot for the time derivative. So what am I saying? Yeah, that's right. And so for H dot, we substitute that expression and we get something like n times KAB plus DANB plus DBNA. And then for the Lagrangian, we get this n times 3R and what else was that? Plus KAB minus K square. So when you now what happens is that so you have, if you look at the structure of this expression, okay, you're going to have a term, you're going to have terms which are proportional to n, right, which will come from this and also from this. And then you will have to get those terms, you have to do an integration by parts. So when you do all this, what you finally find is that your Hamiltonian becomes a sum of three different terms. So again, I'll just write down what those terms are. You get n times, so you get a contribution from the 3 metric here, minus 3R. And then we have something which looks like this, 1 by H by AB, and then minus 1 by half, 1 by 2 H pi square. So this is the term which is proportional to the lapse function. Then you get a term proportional to the shift vector field, which looks like this, 1 by square root of H by AB. And finally, you get a total derivative, 2 times dA 1 by root H by AB. So you can see that it all looks pretty horrendous. And I suppose it's understandable that this is the part which scares away most people from venturing into loop quantum gravity, because usually, you know, the path that is taken is that you have to first do this ADM formalism, then you have to do the canonical quantization and all that before you can get to the good stuff. So, you know, it turns out that, well, to actually understand the state space of loop quantum gravity and the quantum mechanics of loop quantum gravity, you don't need to go through all of this, right? I mean, but I'm going through it because, well, and you know, this is needed to understand where that state space comes from. But in future, when they include loop quantum gravity in the undergraduate curriculum, I don't think they will introduce the ADM formalism before doing so. Okay. All right. So now this is our expression for the Hamiltonian. This is a boundary term. It's a total derivative. And we have two other terms, right? And now I can ask what are the equations of motion and what are the dynamical variables. Okay, so first of all, I can what will be the equations of motion? The equations of motion will be HAB dot, some equation for HAB dot and pi AB dot, right? And again, for these, I would use the usual prescription of Hamiltonian mechanics, which is that HAB dot is this, and pi AB dot is minus delta HAB, right? So this is just the usual Hamiltonian prescription. This set of equations, however, is what gives you the what do you call it, initial value formulation of general relativity. So this is something that is very useful, that is used in numerical relativity. So if you have some general space-time, and like, let's say you want to simulate what happens when two black holes collide, right? And or two neutron stars collide. Well, you start off with some initial time slice, which has those neutron stars, and you specify the metric of that hypersurface, and you specify the momentum of that hypersurface in terms of its extrinsic curvature and so on. And then you can use these equations to find out what is the time derivative of the free metric and the time derivative of the momentum to give you, right? I mean, very roughly speaking, that so HAB at tau plus delta t, right, would be HAB at tau times, H dot AB at tau times delta tau, right? Just the most naive. Of course, in numerical relativity, you have to be much more careful because there are all sorts of issues related to diffeomorphism and numerical stability and so on and so forth. Okay. And then, apart from this, we have constraints. Now, what are these constraints and where do these constraints arise from? Well, this Hamiltonian is a function of h, it's a function of pi, but it's also a function of this lapse and shift vector field, right? So one question that one can ask is, what happens if I do the variation of this Hamiltonian with respect to the lapse, right, and the shift? So delta Hg by delta Na. And the thing you can see in this expression is that this does not contain any derivatives of either n or of the shift vector. So it depends on the intrinsic metric, and it depends on the derivatives of the intrinsic metric, the time derivative of the intrinsic metric. But these two quantities, they are behaving like Lagrange multipliers, right? Because they don't have any time derivatives. So that means, so whenever you have this kind of a structure, right? So you have some Hamiltonian, and I can write it as a sum of some terms like this, lambda ICI, where lambda I, there is no time derivative, right? So there are there is no functional dependence on the time derivatives of I. Then this is a Lagrange multiplier. And what it's telling you is that what it's multiplying is a constraint. So that means this has to be identically 0. Okay. So you can see that, right? Because if you calculate, if you want to find out what is the dynamics of this Lagrange multiplier, you would, let's say, use this expression, right? But since there is no dependence on the time derivatives, right? There is no momentum term corresponding to the lapse and the shift. This expression has to be 0. So these quantities, what it's multiplying, that quantity has to be constant. And so what we find is that this expression is 0. This expression is 0. And I'm going to call it H1, okay. And then this expression is 0. Let's call that H2. So we get these two constraints. This first constraint is what is called the Hamiltonian constraint, which I will tell you in a moment why it's called so. And the second constraint is called the diffeomorphism constraint. Okay. So what will happen when we try to write down when we try to quantize the theory, right? How do we quantize something? We start with some phase space, right? Let's say in terms of some configuration and momentum variables. And then we say that our states are functions on the configuration space. Equally well, you could define them to be states on functions on the momentum space, right? So your states are maps from the configuration space to complex numbers, right? And so psi is some function of the qi. And then in order to write down the quantum version of the Hamiltonian operator, right? You can use the usual prescription, which tells you that, for instance, the momentum operator will be given in terms of the derivative of the configuration variable, right? So the hope is, at least this would used to be the hope, that once you have this formulation of general relativity, when you have this Hamiltonian, right, that one can perform this quantization procedure. But there is a problem. What is the problem? Well, let's say you want to write down the operator for the momentum. Okay, so this operator, let's say, would be something like this. Now, if you try to express the various terms in this Hamiltonian in terms of this, what will happen is, well, one of the things is that you have these factors of 1 by h and 1 by root h, right? And so what is h? H is equal to determinant of HAB, right? So you have to write down h also as an operator, right? So h is so there will be a corresponding operator for this. And your Hamiltonian has a dependence on the inverse of this quantity. Okay. So this means that it has a non-polynomial dependence. So Hamiltonian is non-polynomial. In configuration and momentum variables. Okay. And when you have a Hamiltonian which is non-polynomial, it is generally very difficult to find any kind of exact solutions. So what people tried to do was, well, they looked at specific situations. For example, you can look at a symmetry reduced case.
Deepak,
Yeah.
can you repeat the reason why Hamiltonian is non-polynomial?
So it's non-polynomial because of you can see there's a factor of 1 by h here.
Yes.
Right. So even if I multiply through by this root h, I will get 1 by root h, 1 by root h.
Okay.
Right. So it depends on inverse powers of the configuration variable.
Yes.
Okay.
Deepak, I also had a question.
Yeah.
I have two actually. The first one is, are you ignoring the boundary term in 8G? Okay.
Right. This term. Yeah. Well, for the time being.
For the time being. Okay.
We are assuming that our space-time is asymptotically flat, and that we can drop this term.
Okay. The second question is that I have is that in the Hamiltonian, you do have pi squared terms. For example, in H1, you have pi AB. So that's quadratic in momentum. And then you have trace. So I don't understand why the Hamiltonian is non-polynomial in momentum.
Because, well, it also depends on this intrinsic curvature R, right?
But isn't R3R just does it not just depend on HAB 3R, this Ricci scalar on 3's?
It depends on derivatives of HAB, no?
Yes. Okay.
It depends on derivatives of HAB.
Okay.
And so through that, the dependence on the momentum will also arise.
I see. Okay.
Right.
I understand. Okay.
So what one can hope is that you can look at a symmetry reduced example, right? So instead of talking about the set of three metrics, arbitrary set of three metrics, which is some infinite dimensional space, you think of a space-time. So for example, FRW or FRLW, right? Such that you can write down the metric as something like minus dt square plus at square times dr square. So in this case, now the expressions for your lapse and shift so your shift, for instance, in this case would be 0. And your lapse would be, I think, just A. And your expressions will simplify considerably. Your expression for the Hamiltonian will become much simpler. And then, so your Hamiltonian will become a function of A and A dot, right? Or A and A dot, basically. Those would be the two variables. And then you quantize. Okay. So first you symmetry reduce and then you quantize. And then you get a Hamiltonian, which is tractable, and one can find solutions of that Hamiltonian. So this is the approach which is known as the Wheeler-DeWitt using. Well, the Wheeler-DeWitt equation is general. It applies without symmetry reduction also. But in the cases where you try to solve it, this is how you do it. And so you get some sort of Wheeler-DeWitt equation where A becomes your configuration variable or something proportional to it, and A dot becomes your momentum variable. So again, you get some sort of quantum cosmology, but again, this doesn't seem particularly realistic. And more importantly, because you have done this symmetry reduction before quantization, obviously you have lost out on a great deal of information, right? Because the full theory, so there are two possibilities, right? One is that you symmetry reduce and then you quantize. So you start with GR, right? And then you symmetry reduce, and then you go to the quantum version. I don't know how that happened. The host, I'm the host, right? And I didn't mute anybody, so I don't know how we all got muted. Okay. So these are not going to be equal. So you are doing some sort of quantum cosmology, but I mean, it has a very limited relevance. So this was the condition of the canonical program. It was basically not going anywhere because of the complicated form of these constraints. Right. So you also have to first you have to find the physical states. I forgot to mention that you define your configuration space to be this quantity, to be functions on your configuration space, and then you have to take your constraints. You have to take your Hamiltonian constraints H1 as an operator, and your physical states have to be annihilated by these to obtain your physical state space. So the non-polynomial nature of these constraints makes it impossible to solve them, basically. Okay. At least this was the condition, the situation in the canonical program until the R-Sticker's work. So R-Sticker variables, what is the great thing about R-Sticker variables is that they give you a polynomial, they give you polynomial constraints. And these polynomial constraints, they turn out to be exactly solvable. And when you solve them, you find that your states can be expressed in terms of certain graphs. Well, arbitrary graphs with edges labeled by spins. So there is a bit of a few steps there. And this gives you the final picture. And on these spin networks, you can define area and volume operators. And once you define area and volume operators, you can do things, for instance, like counting black hole states. Which gives you the Bekenstein-Hawking entropy. And the thing is that and it agrees with the Bekenstein-Hawking formula. And so this was done in actually this result by Rovelli and Krasnov preceded Strominger and Waffa's counting of black hole microstates using string theory. But what has happened, unfortunately, is that the string theory community has completely refused to acknowledge that loop quantum gravity has anything to do with reality. For some reason, I don't know what the reason is. Even now, like if you listen to some talks, I listened to some talks 2 weeks ago, and another talk by the same speaker from 1 year ago. And the person claims that loop quantum gravity says, people say that they get the Bekenstein-Hawking entropy, but they really don't. And then the audience laughs. And again, it's very odd because, you know, what we are doing is rigorous physics, right? We're not, and in a way, the physical path that this program is following is much closer to the spirit of gravity than string theory is. Because the path that string theory follows is that you start out with a string on a flat space. Right. So the usual formulation of string theory, or the only formulation that you know of, is completely background dependent. There is no notion of a dynamical geometry. That notion of a dynamical geometry comes from some arguments that you have to do that come later. You say that there is some quantum theory, and then you calculate some beta functions for certain coupling constants, and then you find that those beta functions give you Einstein's equations. That is one way to look at it. The other way to look at it is that one second, yeah. And the other way to look at it is that, well, when you have a string and you look at its excitation spectrum, you get a spin 2 field as one of the states in the spectrum. And now it is very well known from work by Pauly and Fierce, for instance. Pauly, Fierce, these were some of the first people who did this, who showed that, for instance, if you write down the linearization of general relativity, right? If you write down the linear theory, you get a spin 2 field. Now, of course, we study this in any general relativity course, where we find that perturbations of the metric tensor can be decomposed into a scalar part, a symmetric traceless part, and a antisymmetric part. And so this identification of the spin 2 field in the string spectrum, right? This is what they claim gives them the graviton. But again, this is not completely correct, because this simply gives you gravitons in the linear approximation of general relativity. Right? It's not giving you any non-perturbative information about quantum gravity. So whereas the loop quantum gravity program is taking the notion of background independence seriously, right? Which is that our quantum theory of gravity should respect Einstein's equations to begin with, or at least, if not respect, at least they, it should implement them. And then when you go back from the quantum theory to the classical theory, you will get some corrections to the Einstein's equations and so on, which is always the case when you go from classical to quantum to classical. But at least the spirit of background independence should be preserved. And loop quantum gravity succeeds in doing that, because these spin network states, they are absolutely completely background independent. They don't depend on any geometry. In fact, geometry emerges from these spin network states. But there are problems with loop quantum gravity, which is that we don't have a complete handle on how to get a proper classical geometry. So we do get geometry from spin networks, but it doesn't necessarily correspond to a macroscopic space-time. So with some nice properties, at least we have yet to reach that point. But there is so many other things that we have been able to do, which is that we can look at cosmology, we can look at black holes, and we get lots of other agreements. So Deva Malya is asking a question. The two constraints are second class, and Deva Malya, my constraint, this thing is very weak, and I should be ashamed of it. I don't know whether they're first class. So in the constraint program, there are primary constraints and secondary constraints, and then you have first class constraints and second class constraints. So I'll talk more about the constraint, more in detail about the constraints in our next meeting on Monday, on the coming Monday. Today is the 11th, 12th, 14th, on the 14th. Okay. Yeah, Shankar-san, you can please ask your question.
Oh yeah, I was checking whether it was working. So I was asking that near the event horizon of the black hole, the space-time metric is fairly simple, right? It's like an uniformly accelerated Dwindler observer.
Okay. So before we talk about like horizon and all that, like, do you have a question about what we have discussed so far?
Yes.
Is it related to this?
Yes, I was asking just beforehand, like before this. Just can you move your screen a bit above? Yes, sir. This WDW equation.
Wheeler-DeWitt.
Is Wheeler-DeWitt. So you said that in some cases, in some simpler cases, we can use this Wheeler-DeWitt equation. So I was asking whether this is in case of Rindla spacetime, can we use this Wheeler-DeWitt, or can you give any example where we can use it?
Sure, you should be able to do it. Yeah, I don't see why not. Absolutely, and I think that's a really good question. So, but again, off the top of my head, I don't know. I'm sure it has been done by somebody. And if it's not been done, then this would be a great research project. So,
okay. Thank you, sir.
But again, the point is that it will give you non-perturbative information, right?
Yeah.
So, but it will tell you something, that's for sure. So, for instance, you could ask how the Wheeler-DeWitt quantization of Rindler spacetime would match up with how the Wheeler-DeWitt quantization of Rindler spacetime would match up with the quantum field theory on Rendler spacetime description in terms of Bottilov-Bob modes, and according to which you see a thermal spectrum. Observers at rest with respect to that Rendler spacetime see a thermal spectrum and so on, and whether you can relate that spectrum somehow to what you get from the Wheeler-DeWitt quantization. So that would be a very nice thing to perhaps look at. So, I hope I gave you some sort of an answer.
Yes, sir. Thank you.
Yeah. All right. Any other questions? Rajani, Rizwan, any questions? Naveen? No? Okay. So I will, or shall I stop the recording first and then you can ask me questions if that's what you prefer?